The hack computer has a 16-bit arithmetic logic unit. So it takes two 16-bit inputs, what we call X and Y. It carries out an operation on the X and Y inputs and then outputs a single 16-bit value. And then there's also two output flags which tell us about the result. Now the 0 flag and the negative flag. So when the output is 0, the 0 flag will be 1, and when the output result is a negative number, the negative flag will be a 1. So we can see here a picture of the hack ALU. So we've got our two 16-bit inputs, X and Y, and a single 16-bit output we call out. So you can see out is a function of X and Y. So the actual function that the arithmetic logic unit carries out depends upon these 6 control bits. So we've got 6 control bits. Depending on the values we put on those control bits determines which actual function of X and Y will appear on the output. And then we've also got our two output flags, a 0 result and a negative result. So the 6 control bits are shown here. So the ZX control bit, 0 is the X input. So if ZX is equal to 1, we're going to 0 the X input, and X will be equal to 0. So the NX control bits, this negates the X input. So if that's a 1, all the bits what are on X are inverted. So we'll have not X. Similar for Y, we can 0 the Y input with ZY. We can negate the Y input with NY. Now the F control bit, this selects between addition and bitwise AND. So we can either do an arithmetic operation and do addition when F is 1, and if F is 0, we'll do a logical bitwise AND operation. And then finally, with the NO control bit, we can just negate the output. So whatever we get, if NO is a 1, whatever is on the output is negated. So with these 6 control bits, it actually gives us 64 possible instructions. So for the 6 control bits, there's 64 possible combinations for these. So we could actually address 64 different instructions. But actually the hack ALU, we're only interested in 18 of these 64 possible ones. So these consist of both arithmetic operations and logical ones as well, hence the name arithmetic logic unit. And you've seen in the previous slides with control bits, we can negate the inputs and we can also 0 them. But it's important that when you're actually building the hardware, when you're designing this, that we 0 the input before you negate it. So the zeroing operation happens before any negation operation. So this table here summarises the possible operations of the hack ALU. Let's quickly have a look through. So we can either get some literal values, we can output 0, 1 or -1 by setting the relevant opcodes essentially. So for control bits 1, 0, 1, 0, 1, 0, the output will be 0. We can also just output X or Y, so we can essentially just move the input onto one of the inputs onto the output. We can get not X and not Y, -X and -Y. We can also increment one of the inputs, so we can just add 1 to X or we can add 1 to Y. We can also decrement the inputs, so we can just X -1 or Y -1. We can do X plus Y and X minus Y. We can also do Y minus X. And then the last two are the logical operations. We can do X and Y. So normally, as we've seen before, this is we use the ampersand signal here. That's symbol here. That's the equivalent of x dot y. So that's logical and this pipe signal here is for or. So that's kind of x or y. So we'll just use the pipe here. We use these kind of notations because when we normally write the logical or function, we use this symbol. But obviously we don't want to confuse it with addition. So in these ones here, we're talking about arithmetic addition. So we'll just use this pipe symbol to represent or, just so we don't get confused. So these two are logical and an or, and the others were arithmetic. So we'll go through a few proofs of some of these opcodes. So for this example, so we have 101010. So this opcode on the arithmetic logic unit provides a 0 on the output. So it's quite easy to see why. So we've got a value on x. So we just 0x, so whatever the value of x is, it's just gonna, that will just cause x to be 0. This will cause y to be 0, and then when f is 1, we know that f is 1, we're gonna do addition. We'll do x plus y. So obviously here we'll have 0 and 0 is going to give us 0 on the output. Similar for this next example. If it's 0 the y, we'll end up with all zeros on the y input. Then we negate y. So all those zeros will then turn to ones. So we'll end up, y will end up this in binary. So 16 bits all 1 in binary. So this is the equivalent in 2's complement. When you see all ones, this is equal to -1. So this is in 2's complement. All ones are equal to -1. But then we can see we're doing f is 0, so we're doing a logical AND operation with all these ones and x. So for every bit on the input, on the x input, will be ANDed with 1, which is going to leave us just with x. And so for that particular opcode, we'll end up just with x on the output. For this one here, we'll end up with -1. So similar to what we saw before, if it's 0x, so we'll end up with 16 zeros on the x input. Then we negate those, we'll get 16 ones, which is equivalent to -1. Then we can 0 y. So obviously we'll get 0. We do addition, we'll end up with -1 plus 0 gives us -1. So that's why we get that on the output. Another example, this one we get not y. So again, if it's 0 and then negate x, so every time you see the zx and nx, or even zy and ny, when they're both 1, we essentially end up with all ones on the input. And then we do bitwise and with that, we just end up leaving y. And then we can negate the output. So here, we've ended up just with y. We negate the output, and so we just end up with not y. So in a similar manner, you can go through all the other opcodes and work out what you can prove the output. There's some useful identities that you can use when you're doing this. So we've already seen that negative numbers are represented using 2's complement. So this is where we negate the number, or we take the complement of the number. So in this example here, so we negate the number and then we add 1 to it. And we know that's equal to the negative representation of the number. So if we, for example, we wanted -5, we get the binary value of 5. So we know 5 in binary is 101. So we negate that. So 5 in decimal is equal to that. So we negate this. So to swap all the bits, and then we add 1 to it, so that'll be kind of a not x stage. And then we can do not x plus 1. Just add 1 to that, 0. So that will give us the value for -5. So this formula here, we can rearrange it. So obviously we can just rearrange that to give, so not x is equal to -x minus 1. And we can just put the brackets in to say not x equals minus, and in brackets x plus 1. So these are useful identities we can use. So now we look at some more proofs. So for this example, so we're doing not x, that's obviously this part here, and then we're not doing anything to y. All the y control bits are 0, so we've just got y in its own. F is 1, so we're doing addition, and then we're negating the output. So we end up with this expression. So using those identities, if we kind of consider this just to be a variable on its own, so we've got not, so that's this part. And because that was not, we know we can replace it with the minus in front and add 1 to it. So that is equivalent to this. And we can do the same again there. So from with the not x, we know not x is equivalent to this. So we end up with that. Those ones will obviously cancel. And we can just sort out the negative sign in the brackets to leave x minus y. So those identities are useful for proving the rest of the arithmetic logic unit operations. So we'll just look how the arithmetic logic unit actually fits inside the hack computer. So don't worry about all the details yet, we'll cover that later in the course. But at the moment we're just focusing on ALU. So this is a part of the circuit, part of the hack computer that you're building this week. So we've got our arithmetic logic unit with our 2 inputs, x and y. So they actually come from a register, and then this y input, depending on how this mux is configured, we'll either read another value from a register, or we'll read a value from RAM, from memory. But essentially, we've still got our 2 inputs on the arithmetic logic unit, and then the control bits, these feed into the ALU. These are decoded from the instruction. So the instructions that the computer executes are stored in ROM. They go through this decoder, and then from that, the decoder extracts the control bits and tells the arithmetic logic unit which operation to carry out. And then so obviously we get the output of this, and then we also get our 2 flags, so the 0 and the negative flag. These actually feed into the program counter. So this helps to control the fetch logic. So as we'll see later, that's essentially which instruction we want to execute next. So depending if it's 0 or negative, depends which instruction we actually execute next. Because sometimes, we might execute instruction 1, then 2, then 3, then 4, then 5. So sometimes we just scan the next instruction in the memory. But then if we're doing some kind of branch, so some kind of if type statement or something, or a loop, we want to jump to a different instruction. So that these flags we'll see later in the course help to determine which instruction is fetched next.